everyone, how are we doing? I hope the volume is good. I was trying to get the audio working here, just got into the office, and it's time to review. So how about we start with some Chapter 5 problems here. Let me get the notes for the video going right here. Hey, Cameron, good to see you there. Let's throw you some points. I don't have my audio. I kind of reset it from here during the Kahoot. Don't have the current audio in my ears. I can't hear all the point noises, all those things. We're getting the final things. Jennifer, good to see you here. Do you want to do some Chapter 5 review? So how about Chapter 5 practice questions? A lot of people wonder about Chapter 5, so let's go do that. Here we go. Hey, Emma, good to see you there. We're doing some Chapter 5 practice questions over here. I'm going to increase the size of Brian Stevens on the screen. Good morning, William. Good to see you here. How's everyone doing this morning? It is Monday. It's the start of October. Well, the 2nd of October right now. Watch this. There we go. Even bigger on the screen right here, so we can just move across and talk a little bit. So let's start with a question right here with Chapter 5. If you're here looking for some Chapter 5, we got it for you. The first question is going to be, we know that a test in Stat 201 has a mean of, let's say, 70 and a standard deviation of 5. What percent of students would you expect to make above an 80? So if you've done a lot of these, you can probably do this one super quick. Does anyone know it's spooky season, right? Oh man, we got to start playing out Halloween. So if you know how to do these, you might get it super fast. Like you might just be like, who knows how to do these? As Brian resets his audio here. Anyone have a guess at this? Any sort of guess or anything? So above an 80. Oh, Cameron, good work right there, and good work, William. Let's throw you some points. We'll retry putting in the headphones here. So I think you might see it. You both have right answers right there for different questions. So, and Cameron's updating the answer. The best thing to do a lot of times with these is to draw it out. Yes, great job, Cameron, right there. You saw what you did, and excellent work. So we're going to go over here to the draw, and here's Brian's tips for the test. When you get to the test, it updated the pen on me. When you get to the test, the first thing you want to do is probably draw out a normal curve. Now, you don't have to do it first things first. You could do it when you get to a question that asks you a normal curve. You're not allowed to have notes on the test, but you can do a drawing when you get to a question or at any point when you start the test. Now, what am I writing below the curve right now? I would put this on a basic normal curve or a standard normal curve. I'm writing what's below the curve. What am I writing below the curve? What are those values right there? The standard deviations, the z-scores. So those are all the z-scores right there. These do not change. This is the standard normal curve with a normal of 0 or mean of 1, normally distributed with a mean of 0 and a standard deviation of 1. That's what we want to see right there. The first value is the mean, which is mu, and the second value is the standard deviation. So now what I'm going to do is I'm going to take the values right here, and I'm going to use them to say normally distributed with a mean of 70 and a standard deviation of 5. So if you notice right here, you can clearly and quickly see that 80 is a z-score of 2. We'll do a separate question. We'll do some harder ones in a moment. But what you can do is you can now draw on the curve, and you have to think you are looking for this area right here. Since you're looking for this area, we know it's kind of small, but also we know within here is how much area. And so quickly, who knows the answer to this? How much area is within plus or minus 2 standard deviations? Good morning, Catherine. Good to see you there. We're doing some Chapter 5. Within plus or minus 2 standard deviations is how much area? So how much? 95, 68, 95, 99.7. We do the inside-outside trick right here where we say 95 inside, 5% outside, 2.5 on either side. So what I'm saying is 95 is inside of here, 5% is total outside because it has to add up to 100, and then 2.5 because you cut it in half. So that leaves 2.5 right here. And great job. I think other people were getting, if we said below, it would be 97.5. So if you went below, you'd have to add up all those numbers below to say below an 80 occurs 97.5% of the time. So kind of a good warm-up question right there. Drawing the curve is going to be a huge help. But we're just going to keep going question after question. Is that what, do people want to do that? Or do you have other things you want to do? I could just keep going Chapter 5 question, Chapter 5 question, Chapter 5 question. You can pause when you see the question. If you're watching this later today maybe or in the future, you can pause on the question before seeing the solve and see if you can get it. Okay, another Chapter 5. let's raise the difficulty a little bit here. And let's say the amount of M&Ms you get in a bag is normally distributed with a mean of 25 and a standard deviation of 3. What is the probability you get between 25 to 28, 22 between 22 to 28, less than 22, and last but not least, we'll go a little more difficult too. We'll say less than 21, multiple choice question. The last one would be a multiple choice. Who here can get all of these and how quick can you get them? If you can get these in like this, you are super prepared. But see what you get for the first, the second, the third, and the fourth question. See if you can solve them in this moment. They're not too bad. You'll kind of see. I raised the difficulty only a little bit, I think. If these are really tough, don't worry. We're going to practice them and show how to do them all. But what would you get? I'm going to bring it up here so we can see them all at one time. I'm going to draw the curve. So any answers to any of these? They all kind of build off each other, except the last one's a little bit unique. See what you can get. Try to draw out your curve. Draw your curve out to start. So draw out the normal curve and see what you get. Any answers in the chat worth points? So what's the first step? Remember your steps right here. 34, 68, 16. Already got all the answers right there. Cameron, great job, except for the last one, which is going to be a multiple choice, which would be somewhere between blank and blank. We could kind of guess at it. It's going to be about 8 or 9%, I think. But we'll show how to guess at that one in a moment right here. Great job, Cameron. More points in the chat right there. So let's show how to do this. Once again, first step is what? If you encounter a question like this, the first step to solving it is what? If you encounter a question like this, we're not talking about answers right now, we're talking about how to solve. The first step, if you encounter a question like this, is to draw it out. Draw out your curve, put the 0 at the center for the z-score of 0, which is the mean. Start going up and down 3 standard deviations. Your curve doesn't have to be perfect, just has to look reasonable. And now you're going to put the context. The context is going to be the mean given to you and the standard deviation. So we write that it's normally distributed with a mean of whatever that value is. That's the standard deviation by accident. The mean and the standard deviation right there. So we are going to, it's a little bit, good guess is Catherine there too. So I think it's going to be closer to about 9%. We'll take a look at that. So when you do this, we put the mean at the center of 25. Then we go up 28, 31, 34. Then we go down 22, 19, and 16. So the really important one right here is going to be the one standard deviation, which is 68%, which is a number we should know and we give to you on the test. If we say use those numbers to solve it. If we say use the 68, 95, 99.7, use those numbers. 68% of people will get between 22 to 28 M&Ms in their bag. That's what that means, which is plus or minus 1 standard deviation. Great job. Oh, Olivia, that is exactly what I wanted to hear for that last answer. So Olivia's got all the answers right there, and let's show the answers and highlight them as we talk about them. So the first answer right here is between this and this, which is just taking what of 68. Go ahead and say it in the chat for more points. We're just throwing tons of points for following along right here. Using the 68, because I kind of built questions that can use the same number. Just using the 68 rule, it's half right there for points in the chat. So that's the first one. Between is literally the between right there. If you notice the numbers down here, it's the literal between plus or minus 1 standard deviation. So that is literally between. And this one right here, the less than 22, is going to be this right here. Now we could have said more than 22. So if we said more than 22, it would be what? Like just changing this right here, if we said more than 22. So notice how we're at 22, and then we can go more than 22. So if we go more than 22, it's what? And there is the other alternative, solve by subtracting that off. it would be 84. So be careful which way you shade. We just want to make sure a lot of times people will miss something just because they'll shade left or right. But just make sure if it says more than 22, less than 22, draw a little drawing, look at it, and be like, oh, that's a lot of the curve. It has to be, 68 plus 16 is going to be 84, or 100 minus 16 is 84. And great job, Olivia, right there, getting the really tough one. Let's go ahead and give out 500 points. So give some W's in the chat for Olivia right there, because this was the tough one, and Olivia answered the exact answer I would want you to theoretically think on the test. So what Olivia did is they went to the next number, which is 95 right here between -2 and +2. And so 5% on the outside, 2.5 on either side. So what we get is we are looking at this area right here at 21 would be the area here. And what you should notice is 2.5 is too little because that's from here over, and 16 is too large because that's from here over. So the exact knowledge you would have is the answer would have to be between 2.5 and 16. It has to be between those numbers. So that's where we can make a multiple choice question and not give you something exactly on a z-score. So you could get a question like that. I think it's going to be right around 9.3%. Another 500 points if anyone solves it before I do. So this is what you wouldn't do on the test, but I'm going to do it right here with the apps. But who can get it before I can? I'm going to say 9.3. That's my guess. No, 8.8. 8.8. Did Cameron already get it? I'm going to say 8.8. 8.8 is my guess. No one's going to get it before me? No! Someone quick. Someone quick. Someone quick. I say 8.8, did I say? There's the number. So it was 9.1. 9.1. This is using the z-score. Can anyone show me mathematically how I got, and great job right there, we'll throw some more points, or 100 points for you right there. Can anyone show how Brian got the z-score for 21? Take 21, this is another follow-up question, and find the z-score for 21. So take 21, that's 22. Z-score equals observation minus mean over standard deviation. Yep, go ahead and do it. Let's write it here. Great job. This is just z-score practice. Boom, right there. Great job, Olivia and everyone. So we have z-score equals the observation minus the mean over the standard deviation, sigma. So z-score equals, so 1.33 is what it equals, is equal to the observation of 21 minus 25 over 3. And there you go right there. Great work. A lot of people know how to do that. And it can help when you're looking at it to see that this is about where 21 would be. And 21 is a z-score of -1.33. You can also do, if you had the applet, which you won't have during the test, you could do the context version of the problem. I'm going to do a harder one here and take applet pictures now. So once again, I said you could do the context version, which would be this right here. Same answer, but that is still the same z-score. And now you see the drawing we were creating a moment ago. So I'm going to use the same data right here and go to a harder problem. We're going to raise the difficulty again. We're just making it harder and harder until eventually I start stumping people, I hope. If I can't stump you, that is really good news for Chapter 5. This is still the M&M data, right? This is still the M&M data. Okay, still the M&M data. Your friend tells you, this is a very tough question now, okay? Very tough question. Still the M&M data. Your friend is super excited because they got in the 99th percentile of M&Ms. Your friend is super excited because they got in the 99th percentile of M&Ms. How many M&Ms did they get in their bag? Round to the nearest number. Your friend is super excited because they got in the 99th percentile of M&Ms. How many M&Ms did they get in their bag? Use the graphic below. This is a very difficult question. If you get this, your understanding is paramount. You have the highest understanding. Okay, I'll write it on here as you think it over. You have to think what information you're given. So your friend, so what is the 99th? So first off, we'll pause, let people try to solve. I'll throw 500 points if anyone gets this. I'm thinking of the answer here too. Okay, I've got the answer. I'm going to disappear. I want you to take a moment. If you get it, tell me if you use the applet. You shouldn't need to use the applet. This is what you could be provided on the test. So take a moment here, see if you can get it, and then we'll show how to solve it. 500 points first, solve to get it. If somebody gets it, you are allowed to cheat and use the applet right now, round to the nearest number. So tell me what it would be. We'll talk about how to solve this in a moment. Boom, Spencer got it. Yep. It should be a little bit below. It should be like 31.97 or something. I don't know if you use the applet, but Spencer, amazing work, earning everyone 500 points. 31. Did I say 31.97? Is that exactly what I said? Oh gosh. What's going on? My brain's like hyper firing right now. It's like knowledge. So with this right here, let's show how to get it. So did you use the applet or did you solve it with the picture? If you solve it with the picture, amazing. If you solve the applet, still good. Because what are you seeing with the picture right now? What is the picture showing you? By hand, well then you, wow, good job. What is the picture showing you? The picture is showing you, you figured it out, exactly. It's showing you the z-score of the first percentile. So the question becomes, where is the 99th percentile? Well, the 99th percentile is the top 1% because 99% is below it. So if this is the z-score of the first percentile, the z-score of the 99th percentile would be what? If this is the z-score of down here, the z-score over here would just be the what of that. So it would be positive that. So it would just be this, but positive. So that's all it's going to be, 2.36348. And the z-score tells you what? How many whats something is above or below the mean. So the z-score tells you how many whats something is above or below the mean. I'm hoping some people are having some, so I know the z-score, which tells me how many whats something is above or below the mean. How many standard deviations? Now here's what you can do, is if you got a picture like this, you could put the data below here and write 25, 28, 31, and 34. Now if it said round to the nearest number, and this is where you marked, you'd probably be between two numbers. You could also make this a little bit better like that, and you might have a better guess, because now it looks a lot more like that over there. But you probably would guess either what or what if it said round to the nearest number, and this is your context below here. Remember, these are z's up top. That's the z's right there across that line. And then this is the context over here, which is the actual data itself. You'd guess something like 32 or 31. So that's what we would guess if we just looked at this and it said round to the nearest number. I'd be thinking maybe about 32 or 31. So now how do we get it? Well, a z-score, if we look at the formula, is equal to, z is equal to observation minus mean over standard deviation. Now you can reverse engineer this, and if you reverse engineer it, you would multiply both sides, z times that equals standard deviation equals y minus mu, and then you put mu on the other side, and you get that the z-score, so mu plus z times standard deviation equals y. So think about this. You're taking the mean and you're adding to it how many standard deviations it is above or below, because the z-score is negative, you'll go down. So it really just is, how far are you away from the mean in terms of standard deviations? And that's what we will get and solve for the observation there. So using this formula, which is a reworking of the z-score equation, which you can rework right there, re-engineer exactly, and then just think it's like, well, it's the mean plus or minus that many standard deviations. That's what a z-score does for you. It tells you how far away the y observation is. Great job, Olivia, right there. We can plug in the values we have. So our values were the mean of 25 and plus the z-score of 2.3263. Up there, you can see on the top screen. And the standard deviation is 3. And if you solve this out, you will get 31.97. So really good question right there. That is about the upper level of difficulty. If you got this question, you got a very tough one. Are there questions on it? I want to pause because we got time to do a few more here before we take a break before class. This was the upper difficulty of Chapter 5 type questions, but I'm going to do maybe some supplemental ideas in Chapter 5 that we often don't hear. So amazing work if you did that. Really tough question right there. Let's cover supplemental Chapter 5 questions. What is the format of the exam like? Canvas content. Exactly like Canvas content. Canvas content is how the exam looks, and that's going to be your number one way to know what will exam questions look like. About 40-something questions, looks like Canvas content. Number one way to know what the exam looks like. We're going to go over here and do a little RStudio. Is there a way to get additional practice with these questions? Tons of videos. I've got tons of videos where I've done practice questions. Just go to those, pause on a question, see if you get it, look at the solve. But sometimes I slow down and then am I catching back up? Am I desynced? I look desynced in the confidence monitor. Well, we'll just keep working away here. He tagged me one. Yes! There we go. Now I'm resynced. I don't get it. I don't understand. The world's weird. So, so what I'm going to do right here is I'm going to take, let me do it with the easiest example. So this right here is random normal data. 100 observations. How does a normal distribution look? It has two characteristics. Thank you, Cameron right there for, yep, we'll tag people with a bunch of stuff, and that's a great way to put additional videos. So how does a normal distribution look? It has two key attributes. The two key attributes of the normal are that the normal is blank and blank. And here I'll let you see it, and you'll probably be like, oh yeah, great job right there, William, unimodal and symmetric, and there it is. Now that might not look normal. This is because histograms are really bad at showing us how things look because of the way the bins are. So the bins are what collect the data, and if you have different bins, they look different, but random data can sometimes not look perfectly normal. So let's increase the number of observations and we get a much more normal look. That's what we should see. We could go into the weirdness that can occur, but this right here has one mode, it is symmetric, and the more it looks like that, the more normal it is. This is one way to check if it's normal, is to look at the histogram. So you can look at the histogram, see if it looks unimodal symmetric, or see if it doesn't look unimodal symmetric, and you might get something that looks more like this. This is definitely what. These are easier questions right now. We're going to build up the difficulty again, but this is definitely what right here, and you know what time it is. It's Monster Man time. This is definitely what right now. And Monster Man in the chat right there. Cameron's got some Monster Man right there. This is definitely right skewed data, right to the high, left to the low, whatever way the Monster Man's tail goes. Literally, I've had people in graduate school tell me that they never get it wrong in their graduate school questions when they draw their Monster Man. So right to the high, left to the low, and we'll once again repeat if this is your first time hearing this, because right is the right side right there if the numbers are aligned from lowest to highest. Left is down here. This is sometimes called positive skew. This is negative. Just think of the way the number line goes. And these are the high numbers. Make sure you have the high numbers on the high side and the low numbers down here. So if the tail goes to the right, it is positive skew or right skew. And if it is negative, it goes to the left side. Now, what's really awesome is we can actually, can you go over box plots? Yeah, let's do box plots next, which hide important features of a distribution. Box plots hide important features of a distribution. What I really like is we can actually, I think it's library E108, E10. Oh no, do I have the 2 seconds? Where is it? Library moments, cool. Okay, let me get that. I'm gonna have it. Well, now I have it. Okay, so the normal distribution, teaching to this moments, literally moments right here. The skewness of the normal is what mathematically? This is kind of an advanced thing right here. The skewness of a really perfect normal is very close to what? The skewness mathematically of a near perfect normal is close to what? Remember, it has no skew. So the skewness of it is very close to what? The skewness of a normal is very close to what? 0. Now look at this one. You remember how it's going to the right? So mathematically speaking, this is a little more advanced. We wouldn't put this on the test. Mathematically speaking, it has positive skew. But we could also do this right here. You see how that's a positive number? If I take right here and multiply this by -1, we are going to get a distribution that is skewed to the left now. And a left skew has negative skew. So this is why it's called negative skew. Mathematically speaking, when we calculate it, it is negative. And look at how the tail goes towards the lower numbers. This may be helping you out for future, but we can mathematically calculate the value of skew. And if something is not skewed, it has 0 skew. If the tail goes to the right, it has positive skew. If the tail goes to the left, it has negative skew, left skew. So, but there is a mathematical number for this, so you don't even have to argue what way it's skewed. So sometimes my Pearson's like, it's this skew, and I'm like, mathematically speaking, it's actually this. So the next thing we'll talk about here just shortly is 2 other things. Other than just looking at it, how can we tell if it's normal? What are the 2 other ways, other than just looking at it, to tell if it's normal? Like, other than looking at it, we have 2 other ways to tell if it's normal. I know I'm doing this with codes just because I'm quicker with code. We have 2 other ways to tell if it's normal. Normal probability plot, and look at that. Does that look good or bad? This is a normal probability plot where we see what we would expect if normal and what is observed. So a normal probability plot, say it backwards, is a plot that tells you the probability of normal. And as Cameron said right there, that looks very good because it follows the line, and the line is the normal. So the more it follows this relationship, the more normal it is. The more it deviates, like this one right here, the less normal it is. That is very good right there. This one's super bad, and this is our left skew. We got to get Squidward in here being like, Squidward blowing the curve to the left over there with his oboe or clarinet. So I don't know. Squidward plays one of the 2. That is a left skew, and we never go that detailed, but the big thing here is it doesn't follow the line. This is not a correlation. I guess it correlates to the normal, one could say, but we're really not talking in that sense. We're saying, does it follow the normal? So make sure to know that we're saying this does not follow the normal. So now what we would have right here is the goodness of fit test, and this p-value is high. Since the p-value on the goodness of fit test is high, we still believe it's normal. And this is only for, oh, Cameron, you're saying for the next one, right? This one, oh, I should put it on the screen. Let me show you. Right now I'm talking about this histogram, and this is the p-value for this histogram. This is the p-value for that histogram. So Cameron, I think, yeah, no, you're right. This histogram right here, because it's so weird, has a very low p-value, and we would reject normality. Does that make sense? This p-value is super duper low, and we would reject normality for it. So that's a very, very low p-value. So very, very low. Yep, yeah, no, you're talking about this one, I think. This has a low p-value, which means reject normality on the goodness of fit test. And then this one right here has a high p-value, which means don't reject normality. So we'd still believe that this is normal. Let me load up one more thing right here, and I'll show you something really cool. And we're going to do some box plots here. So we are now talking about box plots. Let me go grab a function for it. This is why I love R. I've got so much example code. Whoa. This is side by side within box plots. Okay. Oh, that does not work. That does not work. Okay, let me remove the sup needs to be removed. It doesn't, that's not a good graphic with that. Okay, bad idea. Okay, and then we'll just go color equals, and it's dose. Okay. Okay, now we can do it. Really? Dose didn't like it? Color equals dose? Oh, because there's multiple. Okay, I see it. Hashtag FF8200. There we go. There we go. Okay, so now we have side-by-side box plots. A box plot always shows you the what. What is visible in a box plot, which hides important features that we can only usually see in a histogram. Box plots don't show you everything. Box plots show you the what. Look there on the screen, the 5-number summary. The 5-number summary. So let's zoom in on this one right here. This is why I'm using this right here, because I can zoom around and do things. Here is the 5-number summary of the box plot. The min is the lowest number, the Q1, the median, the Q3, and the max. Now, sometimes median can be called Q something. What do you think median can be called? It can also be called Q what? Sometimes medians can be called what? Q2. Yeah, great job right there. They can be called Q2. What is the IQR for this? So go ahead and mathematically find the IQR for this. What is the IQR mathematically speaking? What is the IQR? What is the IQR? So you want to take these numbers, if I go away, there is Q3 minus Q1. So it should be 5.85 right there, 5.85. Now these whiskers, is this whisker right here the maximum? I think ggplotly can get a little bit mad and show me things, but is this whisker right here the maximum for this box plot? Is that the maximum? Yes or no? Is that whisker the maximum right there? Yes, because there are no outliers. Let me go look at the data set real quick and cheat. Here's the data. I want to go to the, let me go to the 1, there it is right there, and then we've got like 16, so that is 11, here, let's go to right here. There we go, 1, 17, okay. So 17, comma 1, store into 30. So now if you take a look, oh, really? I didn't go far out enough. What? Oh my gosh, I should have calculated where that upper fence is. There we go. So I should have calculated. It's saying I don't like how it says upper fence right there. That is the upper whisker. Ignore that says upper fence. So I don't really love that, so maybe I won't hover over that because ggplotly, you got to update what that says. So look right here. There is a big what right here in the data. What does this represent right here? There's a big what in the data. Think of a G word. There's a big what in the data right here. A big gap in the data. There's no data right there. Is this distribution unimodal, bimodal, or what? Is this distribution unimodal, bimodal, or what? Is this distribution right here unimodal, bimodal, or what? What do you think? It's actually symmetric except for it's mostly symmetric except for the outlier. But here's the thing. Box plots hide important features that we would usually see in a histogram. So if you really want to look at the shape of something, you should make a what? Like, I really don't know if it's unimodal, bimodal, or it looks mostly symmetric because the quantiles are kind of close to each other, like the min, the Q1, the median, like they're the same equal distance, but we don't really have a good idea of what it is because box plots hide important features that we usually see in histograms. Someone's gonna maybe remember that. And so I think I can quickly change this code. We'll cross our fingers to gghist right here. And didn't get too mad at me. We'll see what it does. And it didn't like it. Really, I can't do a gghist like that. It says error must only have one. Well, so we can't do all the variables right here. It's the len, I think, is the one we want. We're gonna go right here and go to len and try this out. And it's mad at me and says, no, you can't do it. That's fine. A warning. No, just give a warning. And it broke. But we won't worry about making all the graphics. Histograms are going to be a better look of what's going on. We could just make a basic histogram right here with df $len, and there it is right there. So it might have some bimodality to it. Maybe there's two peaks. It's hard to say, but very hard. If there were a lot of high outliers, then would it be right skewed? But since there's the really number one way to check out skew is to look at the histogram, and you might just say it has high outliers. Outliers can usually indicate some sort of skewness, but right skew is going to be when there's a what to the monster man, which could be, there could be some outliers over there too. But right skew is when there's going to be the monster man tail, right? And if you're ever really confused on it, you can always mathematically calculate the skewness. If I had to calculate the skewness on this, you see how it has this bump over here? The skewness on this mathematically is probably going to be close to 0, maybe a tiny bit negative, like negative 0.2. Like I said, close to 0. It looks mostly symmetric. Does that make sense? Like I don't really see a monster man here. That bump right there is a little weird, and that's why I said negative, but it's basically 0. Pearson asked by giving a box plot what was confusing. So you can tell with some box plots. Here, I'll draw a few out here. Box plots are not the best for viewing it, but if you had a box plot for this data right here, the minimum is going to be over here. The Q1 is going to be kind of close to there. The median is going to be there, and then you're going to get this, and this would indicate skewness right here. Does that kind of make sense? So when you see this pull on the whisker on one direction, that can indicate skew. So, but the box plot doesn't show everything about the shape. Yeah, so this right here, we would see a right skew, and then if you turn this up, because usually they are put side by side, it would look something like this right here towards the positive side if we had it on a number line going up. I lost that one dot, but it would look like that right there going up. So box plots are not the best way to view the shape, but you can get a good idea. So if Q1 was small and Q3, exactly, that'd be right skewed. You look at, so it's when these distances get really pulled out, it's the more distance you see between it, where, take a look right here, this distance right there, the distances keep getting bigger between these marks right there. So the more distance you have between the marks, then also the high outliers would indicate some sort of skew also. So the bigger the distances, this is going bigger distances on the right side. Distances tell the very, well, so here's the thing, is the percent of data within here and here, here and here, here and here, and here and here are all the what? So how much data is between here and here, right here, this region, and how much data is between there and there? So think about this. At the very bottom, this is 25% of the data down here. Down here in this little region is 25% of the data. Up here in this top region, from the Q3 to the max, is 25% of the data. So think about it, the top part of the data is more spread out, and that goes to the skew, it's pulled in the right direction. So when you see these marks right here between Q1, or excuse me, the min to Q1, the Q1 to the median to Q3, the Q3 to the max, and it's more spread out, that tells you there is a right skew to the data. Does that make sense? That's going a little more complex right there, but all of these regions have the same amount of data because it's all min to Q1 is 25%, Q1 to median is 25%, median to Q3 is 25%, and Q3 to max is 25%, and the top 25% is way more spread out, which would probably denote right about here is the top 25% of the data, and then you can see the compact nature, which is down here. That's the compact nature to the bottom portion of the data, which is all compact, and then the top 25%. So understanding kind of how skewness can be seen in box plots. We don't love seeing skewness in box plots. It's better to look at it in a histogram right there. Lucy, good to see you here. Let's do one more question. What should we do it from? Then we take a quick break, and then we'll come back for some class and review. We'll just do question after question after question after question after question. So join in class. Maybe I'll drop it. No, I can't drop it in the Discord because it's class. But if people join in, I won't drop it anywhere. But chapter 6, let's do a chapter 6 question. So how about I make you a correlation matrix, and I say to you, you know what? There's a psych package for this, which is absolutely amazing. I'll show you psych package correlation matrix. Okay. There's a really good package for this. This question, correlation. So here we go. Oh, man. Here we go. Ooh, I like this. Should use this for my correlations. Okay. ggpairs. Did they turn on their library? Library are they using? Library Coregram. We want a bigger thing than that. ggalley. And let me see right here. Well, yeah, sure. What is the strongest correlation you see right here? So when you hear strongest correlation, you're thinking, I need to look at what right here? This is actually a matrix between every single sort of data, and it includes more than just correlation. It's a pairs between every data point. So you see different graphics from histograms to side-by-side box plots to kind of mosaic plots over there. I don't love it. But what do you notice right here? What do you notice? What is the strongest correlation in this data set? How do you determine strongest correlation? How do you determine strongest correlation? So this is a key topic. The strongest correlation should be the correlation that is closest to what? The strongest correlation is the correlation closest to what? The strongest correlation is the correlation closest to what? 1 or -1. And here's the thing, if I'm asking you, and this is a matrix of more than just quantitative variables, so where can we only see correlation? Think about where you only see values of correlation. And it's doing it on either side where we get to see graphics on one side, different versions of graphics, but you only see correlation when there's what? The scatter plot, right? So what has the strongest correlation right here? Which two variables? If you can name them, they're over there on the side. You have to kind of do pairwise which variables they are. So two quantitative variables. And then correlation is best applied when it's two quantitative variables. We have to have two quantitative variables. When there's a straight line going through the data, and also there's no outliers. Row 2, column 1. So row 2, column 1 right here. Because that is the correlation value right here of -0.868. So it's between weight and, that's not weight. It's weight and miles per gallon right there. Do you see weight at the top and miles per gallon? And so this is a matrix comparing all the values, more than just a correlation matrix. But if you saw a correlation matrix and it said find the strongest, you would look for the one closest to -1 or 1. If it said the weakest, you'd look for the one closest to what? It said the weakest, and I'll make a new one over here because I know some of these other values. We won't use drat. We won't use cycle then. We'll use horsepower and cylinders. So now we get actually a correlation matrix here. And, oh, cylinders are not. They're really... Can I do as.numeric on this? That'd be amazing if I could just turn it numeric here with this. Probably can't. It's mad. It doesn't like that. You have to mutate it. Oh, wait. They're doing that right there. They're changing it to a factor. Okay. Let's not do that. There we go. Now we get a correlation matrix. So now you see an actual correlation matrix right here. We're looking for the one closest to 0 if we want to find the weakest. So it looks like the weakest correlation is between horsepower and drat. And if you go right here and look at drat and horsepower on this side, so we'd need to see the other side of it. Here's drat, here's horsepower. Look at this, it looks a little more random right here. You don't see as strong as a relationship. You see some nonlinear ones, especially here with cylinder and miles per gallon, some nonlinear relationships where it has sort of a bend. And so this is a I'm still zoomed in. A correlation matrix right here. We'll end here in just a moment. But does everyone understand? This is a more advanced correlation matrix where you get to see more of the information to you. This is kind of a density plot of what's going on to look at the bimodality of some data or right skew of some data. For horsepower is right skewed. This one's more uniform. It's got peaks over here, but a little bit more uniform on the data, kind of flat across. And then you can see these scatter plots with the strongest correlation I think we found was between weight and miles per gallon is very strongly correlated with -0.868. And that is still the strongest in this correlation matrix. So correlation matrix takes all the values and correlates them, and we can look at the strength, direction, form, and unusual features. And we'll start here in 15 minutes. So until then, bye for now, everyone. Bye.